So it turns out, and that's really a fantastic result, it turns out that Z has a certain symmetry about it, and it kind of, the first way of expressing that is by saying that it satisfies some functional equation, and that's the equation. So it turns out that for every G, you have this thing. So Z of D is not Z of 1 over Q to the T, because I kind of didn't normalize correctly, but it's a factor times that in a sense, right? So Z of T is, well, there's Q to the G minus 1, T to the 2G minus 2. T is the parameter. You need the degrees to line up correctly. And then you should evaluate Z at 1 over QT. And that holds as like formal power series, not just a particular T. It's the same thing. And that's crazy that it's the same thing. So in order to prove that, of course, we know that Z of T is a sum of, whatever, this 1 over Q minus 1 won't change, doesn't matter. So it's enough to prove that for F and for G separately. And it will hold for both of them then together, any linear combination of them. So let's prove that for F and for G. So let's prove that G is, I'm not going to, G is actually obvious. It's obvious to verify. So I'm not going to verify that G, because G is very simple. This is G. And what you have to do in order to check that G satisfies that is just to plug 1 over QT into G and mess around, and it will work out. Yeah, so it's just not interesting. But for F, it's extremely interesting. So let's do that for F, and then we'll take the break. So what do we want to prove? So again, what's written, I'm going to write this with F instead of Z and kind of develop this thing. So this is this with F instead of Z. And what is F, right? So, I'm kind of ignoring this part for now. And F evaluated somewhere is, again, you go over all classes of degree at most 2G minus 2, Q to the dimension, T to the degree. But T is 1 over Qt in this case. So I just wrote 1 over Qt to the degree. And now if you look at every summand, you get, Q to the dimension minus the degree. And from here, I'm adding up the G minus 1. And T is, you have degree there, minus degree there, and then you have 2G minus 2 here. And my question for you is, what are these expressions, like the exponents? They should be familiar to you. Exactly. So these are the dimension and degree of the canonical divisor. So I'm copying that again. So that's the copy from the previous thing. But now, again, exactly what you said. If you take a canonical divisor, when its degree is 2G minus 2, that was something we proved. And the dimension of W minus C, if you remember, that's Riemann-Roch. That's exactly Riemann-Roch. Written in a different way. It's the dimension of C minus the degree of C plus G minus 1. What we proved is that the dimension is Riemann tells us the dimension is this, the degree minus that, and Roch tells us that this is the correction term. So I kind of isolated the correction term and wrote it like that. So if you now stare again at what was written before, then this is precisely the dimension of W minus C. You see there is a reflection in a sense here. And this is exactly the degree of W minus C, because that's the degree of W and that's the degree of C, and degree is nice. It just adds up. So really what happened was using the Riemann-Roch, and turns out this is equivalent to Riemann-Roch. The functional equation it's equivalent to Riemann-Roch, not just use Riemann-Roch. It turns out that using that, you actually sum up over the same thing. We did something very weird. We started like this, and then we summed over the C's, but with weird degrees and dimensions floating in the exponents of Q and T. But at the end of the day, we got the same sum, like the same summands, and every element here, well, it's not what was written before. There was a dim C and deg C. But the point is that when you do W minus C, you also iterate over all these C's, just kind of reversed. It's a bijection, like W minus C, from this set of classes to this set, because the degree is just flip around by 2G minus 2. So If you have a class with some degree, then that thing will have degree 2g minus 2. So you're just counting backwards. So this is f of t, again. So to sum up, yeah, we proved that for f, but generally for z, we had this functional equation that holds, which is crazy. Yeah. Okay. So maybe just let me finish this slide and we'll take the break. So we are going to use that to prove some very interesting stuff. So just to do that, let's denote by n. So recall that, okay, let's denote by n, I call it n1 maybe at some point, the number of rational prime divisors of the function field. So just note, I just want to know that n is, in our notation of a's, is a1, right? Because an was how many divisors do you have of that degree n, which are non-negative. So for a1 is how many divisors do you have of degree 1 which are non-negative. But that's precisely the prime divisor, the rational prime divisors. Because a little p is non-negative in terms of degree 1. And if you have a degree 1 and you are non-negative, you can't have cancellations. So you are a little p. I mean, you can get degree 1s like maybe 2p minus q if you allow negatives. But if you don't allow negatives and you have degree 1, then you just have to be a divisor that consists of one prime divisor, which is rational. So what I'm just saying is that n, the number of rational prime divisors, which I really care about, is nothing more than a1. Like, generally. And a0 is 1, because a0 is how many divisors you have of degree 0, which are non-negative. So that's only 0. Okay, so just keep that in mind, and after the break, we are going to do interesting stuff. Okay, so let's continue. So just as a recap, we proved the functional equation for the z function of a function field. From there, you can derive the zeta function functional equation. Anyhow, and just to make sure that we understand, n is the number of rational prime divisors. We care much about it now. So that's how many prime divisors do you have. We care about it because this is how many points we have for code evaluations, right? COPA codes. And with the notation that we have, it's a1, right? It's degree 1 divisors, which are non-negative. And again, every divisor of degree 1, which is non-negative, is exactly a prime divisor. Because you can't have cancellations. You have one divisor there, and then that's it. You can't have minuses. Is it okay? And a0 is 1 because there is only one 0 divisor. Like one divisor of degree 0, which is non-negative. There are many divisors, infinitely many of degree 0 divisors, which are not necessarily non-negative. But non-negative, there's only one. Okay. So we have the function equation, we have these two. And also let's denote by z sub 0 the z function of just the rational function field. We know what it is. After we proved that the del is 1, we just showed that it's this thing. But if you're going to look at the z function of a general function field, so maybe I should have done it somewhere before the function field. Oh, I already did it. I just forgot to say. So, sorry, I forgot to have a corollary out to when del is 1. When we prove the del is 1, we have this equation. So z is this thing. So I should have said before. Z is that thing, like 1 over q minus 1, a polynomial plus h times g. And that's the polynomial, and that's g. And if you look at it for a second, I mean, that's a polynomial. And this thing, if you kind of multiply the denominators and do the cross product and so forth, and add it with multiply by h, add f, divide by 1 over q minus 1, you will see that at the denominator you have these things, and by the numerator you have some polynomial of degree at most 2g, because you are going to take this product. Okay, so I forgot to say that, but because of that, you can write the zt, so that's a rational function, but actually all the action happens here in the numerator, because the denominator only has 1 minus t, 1 minus qt, and here it's all the action. So it makes sense to look only at that part, and we call this the L function or the L polynomial of the function field. Because the z function, z polynomial turns out to, not polynomial, the z rational function turns out to be just essentially the L function. and there is no interesting information otherwise. So yeah, and L is the polynomial of degree at most 2g, again, just because by staring at it, when you multiply those, you'll get 2g, and there's also f, but f has degree at most 2g minus 2, so there's nothing that's going to also cancel the 2g, but anyhow, it's degree exactly 2g, really. I'm going to say that anyhow. But I forgot to say that, and now that I'm saying that, Z0t is just this thing, that's what we proved, and because of what I just said, which I forgot to say, you can write ZT, I mean ZT is LT over that, but the over that part is precisely Z0 of t. I mean, if you move things around. So ZT is LT times Z0 of t, or LT, you can write the polynomial, you can write like that. And the reason I write a polynomial as a fraction of two rational functions, which usually doesn't make sense, is just because I want to infer a functional equation for the L function from the functional equation I have for the Z function. Right, so the L function is just this ratio, but right, that's your Z and that's the Z0 of the rational function field. And now I'm using the functional equation for each of them. So the function equation told you should take q to the g minus 1, t to the 2g minus 2, and z of the reciprocal of 1 over qt. So I'm doing it here, and I'm doing it in here as well, but g is 0 here. It's the rational function field. So when you plug g equals 0 here, you get q to the minus 1, t to the minus 2, and then z is 0 of 1 over q to the t. And now that's L, again, like L of 1 over qt, but that's L. So you see, you get a functional equation for the L function. So L of t, it's actually even kind of nicer, is q to the g, t to the 2g, L of the reciprocal of 1 over qt. Okay, so there's nothing there. All I did was to use this functional equation and used it both for the function field I care about and for the rational function field in order to get a functional equation for the L function, or the L polynomial. Because the L polynomial is the ratio between these two rational functions, and I know how they behave under this transformation. So that's what I need from here on, actually. I think we're never going to talk about the Z function or L function. I mean, we don't have much time anyhow, but what we do know is this thing. That's the functional equation for the L function. So, okay, so I just wrote it upstairs anyhow, and we said that the degree is at most 2g. So let's look at the coefficients of this L function. The coefficients of this L function and most of its roots are going to be very interesting. So the coefficients of this L function, let's denote them by small a zeros, a1 up to a2g. Potentially it's 0, but and we have these capital A's which we care about, and these are the small a's of the coefficients of the L function. And if you, I mean, there is this functional equation of that L satisfies, so it must mean that there is some symmetry that the coefficients satisfy. And so let's just see what this symmetry is. So this is the L function evaluated at t. Right? That's how we call the coefficients now. And because of the functional equation, I know that that's going to be the same if I look at q to the g, t to the 2g, and evaluate the same thing at 1 over qt. So that's what's written here, right? It's 1 over qt to the j. I change it to j not to confuse us, but it's all the same. That's the functional equation written in terms of the coefficients. And now what I'm going to do is I'm going to kind of adjoin q to the g and q to the minus j, write it like that. T to the 2g and minus j, write it here. Stare at it for a second and notice, I mean, I want to compare coefficients. It's kind of annoying that it's reversed. So I'm going to define I to be 2j minus g, 2g minus j. And when you do that, so you have t to the I, that's good. It's going to be useful for comparing coefficients. And then here you have a to the, the inverse, so 2g minus I. Now g minus 2g minus I is actually I minus g, right? Because I is 2g minus. And then t to the 2g, that's I did, t to the 2g minus a, t to the I. Good. So anyhow, you just do this thing, index the inversion, and then you can see that you can compare coefficients, and so you get that ai, I wrote it like that. So a to the 2j minus I is q to the g minus I times ai. See, that's the kind of symmetry that you have. the largest and the smallest coefficients are very much related, and also throughout. They are the same essentially if I would have managed to kind of properly normalize things. But this is how they do it, so I'm sticking with that. Okay, so what does it tell us? Well, we have that. And what I care about is what does this tell us about the capital AIs. Okay, you'll see why. But again, the L polynomial, I wrote it with these little AIs. It's a degree at most TG polynomial. In a second, we are going to say it's a degree TG polynomial, even though it also follows from what we did before. And we know that the A2G minus I is AI times Q to the G minus I. And what I want to understand is the capital AIs using the small AIs. Okay? So how would you relate them? Well, I just said that the Z polynomial is the L polynomial divided by that. So instead of writing like that, I'm going to express the L polynomial as 1 minus t, 1 minus qt times zt. And zt holds the capital AI. Right? So zt is capital A0 plus capital A1t and so forth. That's an infinite, that's the z function, that's the infinite sequence, the generating function for the capital AIs. But now let's collect terms. So let's take the products. So for example, the free coefficient, the one with no t's on this right-hand side, is obtained when you take a 1 and an A0. So you have a A0, which I told you is 1, by the way. It's how many non-zero divisors you have which are non-zero, so 1. The coefficient of t is extremely interesting. So it's like minus q, minus q A0. Oh, okay, so there is A1 coming from these two. And then you can take this one and with the t's here. So this and that. So it's A1 minus q plus 1 A0, but A0 is 1. So it's A1 minus q plus 1 A0 times t. And then there are the rest. You can do them if you want, but I don't need them. And as I said, A0 is 1. A1 is how many rational prime divisors you have, how many points you have on the curve. So it turns out that L of t, I mean, even just the first two coefficients, or the first is 1, it's not interesting. But the second one captures a very interesting question. How many rational points you have on the curve, essentially. And for some reason, the mathematics tell you should compare it against q minus q plus 1, which makes sense, because what is this number? Like, this is how many points in what function field? Right, right, it's a rational function field. Right, it has q plus infinity. So any curve is a dimension 1 creature. So this tells you, compared to the simplest, essentially line with the point at infinity, how many points do you have? The end of your n. Good, so A0 is just 1, but A1, the free coefficient of t, not free, the coefficient of the linear part of t is very interesting. And because of the relation that we have, the relation there, you can also extract the largest and second largest easily coefficients. The largest one is going to be q to the g, because A0 is 1. So A2g is going to be like 1 times q to the g minus 0. So in particular, it's going to be a degree 2g polynomial, but you could have seen it before if you want. And this is the most interesting part of it, the A1. You see, it's a very interesting polynomial. For example, when g is 1, hopefully I did it here. Yeah, so I collected it in this corollary. This is what I said. So the L function of a genus G function field, it's a degree 2g polynomial, and it looks like this. So it's 1 plus this very interesting expression times t, plus and so forth, and the largest coefficient is a to the, no, there is a bug. It's just q to the g, t to the 2g. I mean, a2g is q to the g. Good, and we have this also relation. So for example, for genus 1, let's just see what happens there. When you have a genus 1 curve, and look at the L function of that, well, genus 1 means degree 2, because it's 2g. So you have A0, A1, A2. A0 is 1. A1 is this thing. And A2 is q to the g, which is q. So that's the L function of elliptic function fields, for example. That's how it looks like. There's only one interesting part of it, like this one. Yeah. Good. So I know, I think that's cool, but I'm trying to get to the statement of Riemann's theorem. And Riemann's theorem actually, Riemann's hypothesis, talks about the roots of the, I mean, it turns out to be related to the roots of this polynomial. So let's look at the roots of the L polynomial. And actually, it's nicer to look at the reciprocal of the roots. So let's write the L polynomial like that, as a product of 1 minus omega I t. I goes from 1 to 2g. So I'm kind of making the assumption here, but it's the right assumption, that 1 is the free coefficient when I write it like that. But it is. We said that it's the free coefficient. So I can write it like that. And you know, the roots are exactly 1 over the omega i's. It'd be nicer to talk about the omega i's like that. Okay, so let's look at these roots. I mean, they are complex value roots. Everything here is on the complex plane. What I claim, which obviously holds, is that q to the g is the product of the omega i's, and the negation of their sum is this thing that we care about. That's obvious, and I'm going to say why, but that's obvious. What's not obvious and cool is that you can actually pair up the omega i's. You have 2g of them, so you can pair them up such that every pair multiplies to q. That's cool. Like, as complex valued numbers, not just their sizes. Okay, so let's see why this whole thing is true. But okay, so let's see. So this is LT, and we know that the product of the omega i's, I thought this is going to be obvious. The product of the omega i's is just the coefficient of t to the 2g. Like there is also a -1, but it appears 2g times, so it goes away. So it is indeed the product of the coefficients of t to the 2g, and we said that the largest coefficient is q to the g. Right? By the way, the whole we are revolving around even before saying that the omega i's have modulus square root of q. That's kind of what's going on here. You see, I'm telling you more and more stuff that are related to that. So for example, here, you know, when I tell you that these pair are happening, then it means that the modulus of these are, you know, like on average square root of q. Maybe one of them is smaller and one of them is larger, but they want to be of modulus square root of q. It turns out that that's the Riemann hypothesis, the fact that they are square root of q. But you see, these are like shadows of it. Like saying that you can pair the omegas like that, and you know, it could be the case that a pair is such that this is, you know, 1, this is q over 2, and this is 2 whatever. I don't know. But then there is some asymmetry that's going on, and everything is very symmetric, so that's not going to happen. That's the theorem of Riemann's hypothesis. But just, you know, keep in mind, you want to think of them as square root of q's in modules. They sit on the square root of q like sphere in the complex plane. And that's another instantiation. I mean, it's weaker. I'm telling you here that their product is q to the g. You have 2g of them. So, you know, on average, they have a modulus of square root of q. I mean, the pairing argument is stronger, of course. So, but we know that. And we know that their sum, well, their sum is just the coefficient of t, or maybe minus the coefficient of t. So that's why we have minus their sum. Well, that's a1, because that's the name of the coefficient of t in this polynomial. And we said that a1 is n minus q plus 1. So that's, going back, these are the two things I said which are obvious. You know, the product, kind of the trace and norm of these roots give you interesting information. Right, this gives you the genus. I mean, also the degree gives you the genus. How many of them give you the genus? I don't know if it's that interesting. But this gives you something which is highly non-trivial. How many rational points do you have? Like, exactly. It's very weird, right? Like, the sum of complex value function is how many rational points you have on a curve over f5. It's weird. Anyhow, but let's prove the pairing part. Let's prove that you can pair the omega i's together, such that each pair has a q, product of q. So let's see. So that's the L polynomial again. And I'm using the functional equation for the L polynomial, which was that. And now, okay, so what am I doing? So I'm doing the following. So you have q to the g, t to the 2g. So I'm multiplying by q to the g. Right, so now I have qt to the 2g, and I need to divide by q to the g. But I know from before that q to the g is the product of the omega i's. So I kind of write it like that deliberately, weirdly enough. So that's this part. And then L of 1 over qt is just substituting, instead of t, 1 over qt there. So that's what I did here. And now I'm going to push everything into the product. So like qt kind of disperse one qt to every product, to every term in the product. And also I'm going to plug the omega I to the right product. So I'm multiplying every term here by qt over omega I. So that's why you get the 1 becomes qt over omega I, and the inverse of that becomes 1. And I'm doing a fantastic transformation where I multiply everything by -1 2 to the g times. Same thing. It's like -1 times 2 to 2g, but it's the same thing. And now when you stare at it and you stare at that, you see that by doing like q over omega I, 2 omega I, you just permuted things around. Because it's exactly the same thing. Right, so when you consider the action of taking omega I to q over omega I, you get the same product. So it's the same. These are the same. So this is an omega j, or some j, because these are the roots. I mean, the omega i's are the roots there, and the roots here are q over omega I. So as I said, they must be the same set. As a multiset, I mean, they must be the same set, same sequence, just kind of permuted around. Questions? Because that's a bit. It's okay? So it almost feels like you're done, because if these are permuted around, then they are pairs, and that's how you can pair them. Like omega I goes to omega j. So like omega I went to q over omega I, which is an omega j now, because it's another root. So this is the pairing. Omega I go to omega j go to omega I. What's the problem?
We get all the terms.
Exactly, right, good. It could be the case that you are your own pair. That's the problem that could happen. I mean, these are the omega i's, and this is, if you write q over, so I'm saying something simple and I'm somehow managed to make it sound complicated even in my mind. So you have omega 1, omega 2, omega 2g. And then what I did was to note that the q over omega i's are the roots of the same polynomial. So they are also omega 1, omega 2 up to omega 2g. But maybe, maybe this is, let's do it like that. Maybe omega 2 is q over omega 1. And therefore omega 1 is q over omega 2. So they are paired like that. And maybe this is with the previous one. I don't know how, I don't know. But it could be the case that some omega is itself kind of is its own friend. So omega is q over omega. Of course, that can only happen when omega is what? Square root of q or minus, exactly. So there are two annoying omegas that they can repeat. Yeah? So it could be that you have a bunch of sigma square root of q's and a bunch of minus square root of q's that are kind of their own friends, and then the rest which are fine. So we need to make sure that we can pair them. We really need to make sure there is an even number of each of them. If there is an even number of the square root of q's and of the minus square root of q's, we are fine. Especially the minus square root of q's. The square root of q's, I can join themselves if I want, but let's say the minus square root. Okay, so this is what I said before. So if you rearrange, the annoying thing is that you can have fixed points, but there is a non-fixed point part, which could be empty, and then the fixed point. So let's say that up to k, everything is fine. Omega 1 is coupled with q of omega 1, which is different. And omega k is coupled with q of omega k, which is different. And so k is at most g, of course. But unfortunately, there could be like m copies of square root of q, like m of the omega i's are going to be square root of q's, and n, I don't know where it's written, but n, yeah, here, n of the omega i's are minus square root of q's. So what do I know? I know that 2k plus n is 2g, because I have 2g elements, and they are paired together and so forth. And I really want to show that both of them are even. Maybe just even n, but let's prove that both of them are even. And actually proving that one of them is even is proving that both of them are even, because there's some is even. So let's prove that n is even, and therefore m is going to be even, and then we're done. So why is n even? So let's go back to this is why I needed that. Let's go back to the product of the omega i's. On one hand, we just proved it's q to the g. On the other hand, so let's see. So every pair here gives you a q. So it's q to the k, number of pairs. And then you have a q, like square root of q to the m, because the m's are the positive one. Square root of q to the m's. And then you have each of the n minus square root of q's give you a minus square root of q to the n. So I can write it as minus 1 to the n, q to the n over 2. There is no issue, like there is no square root on the minus 1 or anything, just like it's minus square root of q to the n, so it's this thing. And now if you stare at it for a second, the exponent of the q's, so k plus m over 2 plus n over 2, because of that again is g. So q to the g is minus 1 to the n times q to the g, so n is even. So everything's fine, and they're all happy. And you can actually pair them together like that. So we have, sorry, yeah. Where is the proof? Yeah. So we have this thing. We know that we can pair the omega i's in such a way that it's kind of very symmetric. You really want to say that all of the omega i's have modulus square root of q in a sense, because I mean it's so symmetric. It will really destroy it if one of them won't have a square root of q. Yeah, and that finally leads me to the statement of the Riemann's hypothesis. It takes time just to get there. Yeah, so, right. So this is the Riemann hypothesis, which is a theorem. It's the Hasse-Weil theorem, Hasse-Weil bound. It tells you the following. It tells you the following three conditions are the same, and all of them are, it's a theorem. It's a big theorem. I'm not going to prove it in 25 minutes. I could prove it like 4 hours, by the way. I mean, we're not far away. It's not like another course. Just, given the 3 hours of the constant function, so 7 hours. But it took 4 hours last time. So just not just a number, it's really what happened last time. So, but in the projects. Anyhow, so it turns out that all of these equivalent condition holds, and the fact that they are equivalent is not hard. But, so it turns out that the root of the zeta function all lie on the on the line. Yeah, that's okay. Like in the line where the real s is half, I should have said real s. Where the real s is half, this is the Riemann hypothesis. Like when you replace this with the usual zeta function. Here you don't need it, yeah. Right, yeah, here it's not a problem, right? There you have the non-trivial, the trivial zeros. But yeah, here I think that's what you have. Another way of saying that, just because q to the minus s is t, the roots of zt, that's what we said all the time, all lies on the circle of radius q to the minus half. That's what I told you. They should have like the omega i's should have modulus square root of q. And the omega i's are the inverse of the roots. So the root should have modulus 1 over square root of q. Everything seems to suggest that because they paired up in such a way and so forth. So that is true actually. That's a theorem. And yeah, that's what I said here. It's the same thing. These are obvious. The equivalence is obvious, but the proof of any of them is not. So the omega i's, all of them have modulus square root of q. Okay, so I'm not going to prove the theorem, but at least we know what the theorem is, and I do want to tell you a bit of the proof. Like, it's really the beginning of the proof, but it gives you a lot of insight about what's going on in the proof. And I actually think the cutoff is nice because for 15 minutes everything makes sense, and then it doesn't. It's kind of you don't understand what's going on, like in the proof of Riemann-Roch in a sense. You just do things and it works, and I can't give you much intuition about it because I don't have it. But at the beginning, I do understand what's going on, so I can tell you, I can actually stop exactly at my knowledge, real knowledge. So, for example, this is a theorem, and the important corollary out of it, which is actually, okay, corollary out of it is this thing. I'm going to prove that, it's like 2 lines. But the corollary is that if you ask how many bless you. How many rational functions do you have in your function field? Well, it's q plus 1 plus minus 2g square root of q. That's what I told you. That's kind of the Hasse-Weil bound. That's the Hasse-Weil bound, and that's the Hasse-Weil theorem in a sense. But that's the theorem that we talked about. I told you later that asymptotically, as the genus grow, you can get rid of the 2 even. But for any genus, this is the result. Remarkably, it's equivalent, essentially equivalent. We'll talk about it in a second. It's equivalent to that, morally. Like there are quantifiers issues, but okay, we'll see in a second. But this is a kind of this is a very interesting thing, right? How many rational? This is a very deep thing. How many rational functions your curve has? Well, that number. You should, when g is small, you should think of it as kind of standard deviations. So it should be q of q plus 1, and it is up to 2g standard deviations. In our case, by the way, g is larger than q. G goes to infinity, q is 7 or 49. So we don't view it as a standard deviation. We care about it more than we care about q. And that's why we care that in the asymptotics, it's not 2, it's 1. Because we really want to understand that. But regardless, you have that. And why this follow immediately, by the way, from what we did, or not from what we did, from this theorem, and what we did, because we know that the sum of the omegas, or their negation is a1. And if you remember, a1 was precisely this n minus q plus 1. So this means that n minus q plus 1, if you just do a triangle inequality here, it's the absolute value of this sum, and by the triangle inequality, it's the sum of the absolute values, like the modulus, complex valued modulus. And that's it. You have 2g summands. Each of them is by the Riemann hypothesis, or the theorem there, theorem 18, under well called is square root of q. So you get 2g square root of q. That's it.
Theorem 19 just assume one of the three.
Right. Yeah. So here I'm kind of using that, but they're all the same. They're easily. Yeah, and the equivalence is easy. Yeah, and I didn't even do that because it's just like moving parameters around, like t to q minus s. But you see, this tells you that like, so you don't even need. So this theorem looks much weaker. You don't need to understand the omegas. You just need to know that they are bounded, and even in an amortized sense, it would have been enough. But we actually, the Riemann hypothesis tell you a bound for each of the sums. So it doesn't seem like this should imply, by the way, the Riemann hypothesis, because it's too weak. And it doesn't, but something does, something very much related to that. But anyway, that is useful for our course, because we do need to understand that. So when you want to prove the version without T2, you use this in a different way, not like that. It's not so hard. It's harder than 2 lines, but it's like 2 pages. Yeah. Okay. Yeah, so this is my apology. You see there is an apology here. It looks like just formal stuff, but it's apology. So, because we haven't done constant field extensions, because it will take 2 to 3 hours, and I need like 3 or 4 more hours to prove the Riemann hypothesis, so I'm not going to do that because 20 minutes left. But we are not far, and I just want to give you some taste of what's going on. So for example, the fourth step in the proof, and the first couple of steps are the following, and I'm going to prove some of them. Right, so it's kind of obvious. See, it's a one slide which we are going to go over. It's kind of obvious that the L function of the extension of constant field extension, the RF extension, is very much related to the original function. It looks exactly the same when you look at the roots. The L function was 1 minus omega I to the t. In the RF extension, it's just going to be 1 minus omega I to the r to the t. It's extremely simple. So constant field extensions reflects very nicely, very simply in the L function. Just this. Like in the zeta function, in the z function, it was more complicated. Z of t to the r was this product of all r fruits of unity and so forth. In the L function, just you know the root of the L function, you know the root of L2. Like same roots essentially, just take to the power r. Just let's see the proof because it's easy. So in the proof, you do start indeed from what I said before, the relation of the z functions the ZR function and the Z function of your original function field. And then you just kind of massage it a little bit. So maybe just let's do it. So the L function applied to T to the R, right? It's the Z function, the R of Z function to T to the R, divided by the Z0 function of the rational function field. Because L is Z over Z0, also with R's. And for the Z functions, we have this equality, right? So ZR to the TR is this product. I think I changed for some reason zeta to whatever this letter is, but don't worry about that. It's a new slide. So, and also here. Yeah, it was late. So good. So now you can, instead of taking the ratio of products, you can take the product of ratios, and every ratio is exactly the original L function applied to zeta t, right? And this thing is that, is this thing, right? Written in terms of the omegas, right? So L of t is the product 1 minus omega I t, but t is zeta t. And now if you flip the product, like everything is finite here, the product symbols here, and you stare at this for a second, like forget about the I, fix an I. So this, the product over all R future infinity of this thing is precisely that thing. I mean, that's the trick. And you actually know that. I mean, there are many ways of seeing that, but the best way is that to know that this is essentially the same thing as saying that formally this polynomial is that polynomial. Like TR minus 1, the roots of this thing are all the R roots of unity, and that's what's written here. Same here, but you need to kind of weight it back and forth by omega I. Don't worry about it. Just a calculation. But what you know from that is that omega I is equal to Q, square root of Q, if and only if omega I to the R is equal to the square root of Q to the R. This is just because, I mean, that's obvious, but these are the roots of the L functions of the R extension of the function field. And so this tells you that the in particular part, which is more interesting, that if you want to prove the Riemann hypothesis, it's enough to prove it. I mean, once you prove it for some function field, you prove it for all of its extensions, the constant field extensions. Because the Riemann hypothesis tell you the roots are square root of Q in modulus. But when you go square root of Q, but when you go up to an R extension, Q goes to Q to the R. And we just saw that the omega i's go to the omega I to the R, so the modulus also go by a factor of R as they should. So if the Riemann hypothesis was, going backwards, that the omega i's are the square root of the Q that you care about, then once it holds for all extensions. The reason it's useful is because sometimes you're missing stuff in your field and you want to look at extensions. It's like the best thing after moving to algebraic closure. Like look at extensions, and that's useful. You go to a higher field, to a field of larger size and extension, prove the Riemann hypothesis there, and deduce it here. So that's why we really like this, not this theorem, in particular the in particular. And just to give you another flavor of, you just do a bunch of reductions. So here is another reduction that you can do. So instead of proving the Riemann hypothesis, you can actually prove what I told you is a corollary of the Riemann hypothesis, but not quite. So what is true is that if you prove that there exists some constant, it doesn't have to be like 2G or what was there before, any constant that you want, any number. But for that constant, you can prove that for every R, that's the extension of the constant field extension. For every R, you have this bound that was a corollary from before. So NR, which is how many R rational points you have in the extension, the R extension, minus what it should be. Well, the corollary was it at most 2G times square root of Q, or in this case Q to the R over 2. So if you can prove that bound, not the Riemann hypothesis, just that bound, but you see, you are allowed to choose any C that you want. It doesn't have to be twice the genus, which is fantastic and weird, but you have to do it like uniformly. So C should work for all R's. So if you can prove that, then you prove the Riemann hypothesis for the original function field over FQ. Very strange. Like, how could you infer, like, how C goes away and you get 2G? Like, it's magical that you get, you can prove it with 4G and it will hold for 2G, just because the theorem. And I'll show you, it's like one slide. But it's fantastic, and it uses, again, analytic machinery, which kind of doesn't care about numbers. They care about poles and stuff. So you'll see, it's one slide, but you like, yeah, okay, not one slide, but not too many slides. And it's remarkable. It's crazy. But that's what I meant when the corollary implies the theorem. It doesn't, but if you prove that there exists a C that holds for all R, then you're fine. So let's prove the proof of that, and maybe I'll set one more theorem and we'll finish. Yeah, so the key idea is to consider this function out of the blue. So let's consider m of t. Well, I don't really care about this negation, but it's always there. So the negation of this thing. Right, so you create a rational function that has poles at the 1 over omega i's, like simple poles there. This should be like a complex field, not C. Okay. So, at 0 it's 0. No, at 0 it's a number. It's a minus 2g or whatever. But it's not. It's defined. So it's definitely holomorphic, namely like differentiable around 0. And actually, the first place which is not going to be, which has a singularity when you move away from 0 is where? So maybe let me draw a picture. So you have like this is the complex plane, and this is 1 over omega 1. This is 1 over omega 2. Maybe this is 1 over omega 3. And these are poles, simple poles of that function. So here everything is, great and nice. And as you go away, the first time you hit an omega or an inverse omega, you are not. I mean, the convergence radius is not. I mean, you are defined here, but you are not defined here. You can't be defined over the entire ball of this radius, which is larger than that. So the convergence radius, I mean, what's the biggest ball that you can be differential over, is obtained by the minimum of those. I think. Yeah, good. Like the absolute value, how far this is from the origin. So keep that in mind. On the other hand, completely independent of that, let's Taylor expand MT. Okay, so let's go back to MT for a second. So I want to expand this thing, just, this is a geometric sequence. And this is a sum of 2g of them. So I'm going to write the 1 plus t squared and so forth, but with the omega i's, and sum up the 2g summands, and switch the sum. So, right, so this was outside with the minus, and then instead of writing 1 over omega it, I'm writing 1 plus omega it plus omega it squared, and so forth. And I'm exchanging the sum because we're running out of time. So anyhow, you get this expression. You get the coefficient of t to the r is this thing. But that is something we know. Like the sum of the omega i's, or the omega i's to the r, or the minus of that is you know exactly what it is. It's how many rational points you have after you extended your field to fq to the r, compared to what it kind of should be in a sense. Like that's we proved. We proved that for r equals 1, but then we proved that omega I to the r is exactly the omega i's that you look at when you look at this thing. So you can actually replace these summands with that number, with these numbers. So you get this. Okay. So I just copied it again. And now, so far I never used any assumption. But per our assumption, we proved that there exists a C, such that for every r, again, it was a uniform bound. For every r, this difference is bounded by C times q to the r over 2. And again, remarkably, C has, you could do whatever you want with this C. Right? I don't know. But regardless of what C is, just because you can look at this and ask when does it converges, I mean, C doesn't really affect the convergence of that thing. That's the point. It converges once t is, whenever t is smaller than q to the minus half. Right? Because this thing, you should replace it with that. So you have this times t to the r. So once t is smaller than 1 over square root of q, like strictly smaller, you're fine. It's going to be a convergence, like a geometric series that bounds your series and everything and then by convergence of absolute value, blah blah blah, your series also converges. So once t is smaller than q to the minus half, importantly, without any dependence on c, as long as c doesn't depend on r, at least, this sequence converges when t is bounded by q to the minus half. So it really means that the convergence radius of this series is at least q to the minus half. But it was at most the minimum of the omega i's inverse from before, if you remember. So you see, C disappeared here at this point because it doesn't affect the convergence, and the proof is via convergence arguments. So anyhow, you look at that and you see, well, it just means that all the omega i's are smaller than square root of q, because it just like that. But the product is q to the g. So none of them can be strictly smaller than square root of q because one of them will have to be larger. So actually, all of them are of size square root of q in modulus, and that's the Riemann hypothesis. So, I don't know. It's like a weird argument like that. Anyhow. So that's kind of how the proof begins. And then I'm not going to do that. But the last theorem here, which actually haven't finished because I still have 2 more slides to write, and I imagine I won't get to that. But I do want to upload it as a video, so I'm going to do it. I just give you one. I'm not going to do it now, but here is one version of something that you can prove. And actually, that's what you prove at the beginning. So this is the proof of the Riemann hypothesis in some relaxations, and maybe I'll just state it. So it tells you that, in a situation in which Q is actually an even prime power, that's fine, I don't know. But it has to be much larger than the genus, which is exactly not what we are interested in of. For us, Q is 49 and genus goes to infinity, but still. And under the further assumption, which is not always true, that there is a prime divisor of degree 1, we know there is a divisor, but not a prime divisor of degree 1. Under all of these assumptions, I can give you one-sided bound for the upper bound. And that's essentially the bound you want. You shouldn't worry about the 3 plus 1. You can make it a 2G because essentially what we kind of said. But so that is something that we can prove in half an hour. I mean, just calibrating you. And then what you're going to do is you're going to prove a lower bound based on the upper bound, and then combine them with the previous theorem that tells you don't worry about C. Don't worry about moving to higher extensions because you can go back and somehow you get the Riemann hypothesis. But for me, it becomes very algebraic, many Riemann-Roch spaces, stuff like that. It was late at night yesterday, so I'm not sure it's right. Yeah, anyhow, so I'm not going to do that. I was hoping, up until 2 or 3 weeks ago that we'll be able to do that, but the hope went away. So that's it. So the next part is on you, to do the project. It's really nice. Last time it was crazy. It was 30-something hours. Many people came to a lot of the talks, which was really nice. And I encourage you to do so because they are interesting. The topics are interesting. I don't know if the talks will be interesting. It's up to you. So I'm not going to summarize what we did because that will take half an hour, essentially. We did a lot. I hope you enjoyed it. It's like a kind of uncomparable amount of math for a CS course. So either I am sorry or you're welcome. Good, and hope you enjoyed it. Yeah, that's it.